All right, today we're jumping into a classic problem from Irodov. One of those mechanics puzzles that looks absolutely impossible when you first read it. But trust me, if you look at it the right way, it just clicks. So, you ready to break this thing down?
So here's the scene. Imagine a little disk, mass m, just sitting at the top of a frictionless hill. The hill's got a height h, it starts from a dead stop, slides all the way down, and lands on this plank, mass m, that's just chilling on a smooth floor. The second that disk hits the plank, friction wakes up. It starts grabbing at the disk, slowing it down. But at the same time, it's pushing the plank forward, speeding it up. This goes on for a bit until finally they lock in together. They stop slipping and start moving as one solid piece at the exact same final speed. And this is where you might get stuck. I mean, the question is about the work done by friction, right? And work is just force times distance. But wait, we have no idea what the friction force is. They didn't give us a coefficient. We also don't know how far the disk slipped, or for how long. So how in the world are we supposed to find the work? It feels like we're missing all the key info.
Okay, this leads us to the big trick, the key insight. In physics, a lot of the time, the secret is all about choosing your system correctly. So instead of thinking about the disk or the plank, let's try thinking about the disk and the plank together as one thing.
And here's why that's so powerful. Think about that friction force. The plank is putting a force on the disk, and the disk is putting an equal and opposite force back on the plank. From the outside, those forces are invisible. They're internal to our combined disk-plank system. It's just them interacting with each other. And because they're a perfect action-reaction pair, they completely cancel each other out when we look at the system as a whole. So if the internal forces cancel out, what about external forces? Well, we've got gravity pulling down and the floor pushing up, but those are balanced. And horizontally, the problem says the ground is smooth, so there are literally no external forces pushing or pulling our system from side to side. And whenever there's no net external force, you know what that means. Momentum is conserved. This is the magic part. We can find their final speed without knowing anything about that messy friction. So, what's the momentum at the start? It's just the disk moving, so mv. And what's the momentum at the end? Well, now they're one big object with mass m plus m moving at some final speed v final. We just set those two equal and boom, we have our final velocity, or at least a way to find it.
Okay, that's great for the velocity, but the question wasn't about velocity, it was about the work done by friction. So how do we get there? Well, this is where we have to shift gears and start talking about energy. Because whenever friction is doing its thing, you can bet the kinetic energy of the system is changing.
Now here's a huge trap that so many students fall into. You learn about conservation of energy and you want to apply it everywhere, but you can't here. Why? Because of friction. Friction is what we call a non-conservative force. It basically sucks mechanical energy out of the system. But that energy doesn't just vanish into thin air, right? It has to go somewhere, and in this case, it turns into heat. So while mechanical energy isn't conserved, the total energy of the universe, including that new heat, always is.
And that is the final piece of our puzzle. It's all about the work-energy theorem. It tells us that the total work done is simply equal to the change in kinetic energy. So, the work done by friction in this case is exactly the amount of kinetic energy that disappeared from our system. All we have to do is calculate how much kinetic energy we lost, and that's our answer. Okay, we've got the concepts down. Let's do the math and put some letters to this.
Step 1. We need to know how fast that disk is moving right when it hits the plank. The hill was frictionless, remember? So this is a straightforward energy conservation problem. All the potential energy at the top, mgh, gets turned into kinetic energy at the bottom, 1/2 mv squared. A little rearranging and we get v squared is just 2gh.
Okay, step 2. Let's look at the kinetic energy of our whole system. Initially, right as the disk lands, all the kinetic energy is in the disk because the plank isn't moving. Finally, after they're stuck together, the kinetic energy is in that combined lump of mass moving at the final velocity we figured out earlier with momentum.
And now, for step 3, we just put it into the work-energy theorem. The work is just the final kinetic energy minus the initial kinetic energy. And think about it. We know energy was lost to heat, so the final Ke has to be smaller than the initial Ke. That means our answer for work should come out negative, which is exactly what we expect. Friction does negative work. It takes energy away.
So we plug in our expressions for the velocities, we do a bit of algebra, and what you find is that a whole bunch of stuff cancels out. And what we're left with is this beautifully simple answer. Look at that. The work done by friction has nothing to do with the coefficient of friction or how long it took. It just depends on the masses and the height the disk started from. Kind of cool, right?
All right, but we're not done yet. Part 2 of the problem is a real brain teaser. It's one of those deep conceptual questions. What if you weren't standing still watching this? What if you were on a moving train watching it all happen? Would you get the same answer for the work done by friction? Let's think about what that question really means. The work done by friction turns into heat, right? You could literally measure the temperature of the disk and the plank going up. So the question is it possible for me, standing on the ground, to measure a 2-degree temperature rise, while you, flying by on a train, measure a 5-degree temperature rise? Could the physical heating of an object depend on who's looking at it?
This is a really subtle but crucial point in physics. Things like velocity and even kinetic energy, they absolutely depend on your frame of reference. They are relative. But the amount of energy lost to a process like friction, that change in energy, that is something that everyone agrees on. It's what we call an invariant quantity. As long as you're not accelerating, every observer will measure the exact same amount of energy dissipated.
Yeah, think about it. The heat generated is a real physical thing. It's the atoms inside the disk and plank jiggling around more violently. That's a physical state, and that state can't possibly care if the person measuring it is on a train or standing still, so the short answer is no. The result is absolute. It does not depend on your reference frame.
Okay, let's just step back and review the game plan we used here, because this isn't just a one-trick pony. This strategy is something you can put in your toolkit for all sorts of mechanics problems.
First, define your system carefully. By grouping the disk and plank together, we made friction an internal force we could pretty much ignore. Second, always be on the lookout for conserved quantities, like momentum in the horizontal direction here. Third, when you have non-conservative forces like friction, the work-energy theorem is your best friend. It lets you find the work done just by looking at the change in kinetic energy. And finally, remember that physical realities like energy lost to heat don't change just because you're moving. This whole approach is your secret weapon.
So that really is the big takeaway here. So many physics problems that seem impossible on the surface, they just crack wide open if you take a moment to ask yourself 2 simple questions. What is the smartest way to define my system? And based on that system, what physical quantity is being conserved? If you get in the habit of thinking that way, you'll find there are very few problems you can't tackle.